Hi everyone, welcome back. Today I'm going to be running through a past paper for Test 2 for you guys. This is the Test 2 from 2014. This is the exact test that I did when I did my Stats 1000 course in 2014 at UCT, so I have very fond memories about this. Let's jump straight into the questions. Question 1 doesn't relate to any question, it just says what test we're doing. We're doing test A, so don't worry about that. Question 2 is our first proper question. We've got two normal distributions, A and B, A being the solid line, B being the dotted line. Which of the following statements is true? A, the probability that B is less than 10, so all of this area, is less than the probability being less than 3. No, not quite. This area is definitely not greater than all of that area. So not A. B, the mean of A is greater than the mean of B. We can see the mean is going to be the center part of these distributions. B is definitely greater than A, not the other way around, so that is false. The variance of B is smaller than the variance of A. Also not true, because if you look at how spread out B is definitely a lot more spread out than A. A is a lot more pointed, and so the variance for B is definitely going to be greater than A. So C is also not right. D, the probability that A is greater than 3, so from here, there, so this area over here, is less than the probability of B being greater than 3, so all of that. That is true, because this area, all of this area, is greater than that area over there. So our answer for question 2 is D. Awesome. We now move on to question 3. Suppose we have a random variable x. Right, and x has the U distribution, so uniform distribution, with parameters 12 and 22. So we know that x follows a uniform with 12 and 22. Okay, awesome. Probability density function, PDF of x, can be expressed as which one of these? So we literally just have to find out what the probability density function is with these parameters. Right hand side all the same, so don't even consider it. We're just going to be looking for these values. Now if you recall, the PDF of a uniform distribution is just equal to 1 over B minus A. B and A are the values we have. B is equal to 22, A is equal to 12. Therefore, B minus A is equal to 10. So our PDF is equal to 1 over 10. Now, do we have that as an option? Yes, we do. Sorry, I've just left my pen. There we go. So, there you go. C is our answer. 1 over 10. 1 over 10. Perfect. Now moving on to question 4. A biased coin is 3 times more likely to land on heads than on tails. Okay, so we have a ratio of 3 to 1. 3 times the probability heads, 1 time the probability tails. So sorry, that's heads, that is tails. So the probability of getting a heads is going to be 3 over 4, because the total is 4. Probability of getting a tails is 1 over 4. Now, if the coin is tossed 8 times, what is the probability of observing exactly 6 heads? So they're now asking us, if we toss the coin, this biased coin with these probabilities, 8 times, what is the probability of observing exactly 6 heads? Now, what kind of distribution can we apply here to this question? And the one that I'm thinking of is the binomial distribution, because we have either heads or tails. We do the test multiple times, and we want to know the probability of getting exactly 6 heads out of these 8. So we're going to be looking for a binomial distribution setup with 8 choose 6, right? So we're cutting down into B, D, or E. We've got the probability of a head being 3 over 4, and we want that to be the power of 6. And there you go. That's jumped out to me immediately. These are not 3 over 6. This is 1 over 4, so that's also not right. So we are looking for B. Exactly 6 heads out of 8 tosses. The probability of getting a head to the power of 6, the probability of getting a tail to the power of 2, right? Because it's 6 heads. And there you have your answer. So we have B for question 4. Question 5. The lifetime of a certain graphics card is exponentially distributed with parameter lambda is equal to 1 over 5p or 0.2. If you purchase one of these graphics cards, there's a 55% probability that will break within question mark. So we need to find, if we've just bought this graphics card, what and how many years will, from the beginning to the year that we're looking for, this year K, there's a 55% probability of it failing, or yeah, that will break. They've given us some interesting answers. I think the best way to start this is to think about, you're going to be integrating from 0 to question mark or k. We'll let k be an unknown. We're going to set up our exponential distribution because we know it's going to be exponential. We're going to have 1 over lambda times e to the negative x over 5 dx, and that is going to be equal to 0.55. So we're looking for the starting point 0 up until what value k, right? Is the probability going to be 55%? We know that's going to be 55%. We just don't know what k is. So through doing this, through evaluating this integral, we should be able to have a path to finding out what k is, if k is this unknown. So we're going to jump straight into it. If you recall, the integral will just be equal to e to the negative x over 5 for the values of 0 and k. It's equal to 0.55. We can pop in our values. We're going to pop in k. K is going to be negative, so I think we're going to switch this one around. We're going to look at 0 first. So e to the power of 0 becomes 1. Minus, because we're looking at positive and a minus, so that becomes negative. E to the negative k over 5 is equal to 0.55. Now if we take the 1 across and we make it positive, we end up with e to the negative k over 5 is equal to 0.45. Right, so if we go minus 1 on that side, that becomes negative 45. We want to cancel these negatives out, it becomes 0.45. Now, what do we do from there? So, what we're going to be doing is, I see I've run out of space, so I'm just going to write this again. We've got 1 minus e to the negative k over 5 is equal to 0.55. We take the 1 across, so we end up with negative e to the negative k over 5 is equal to negative 0.45. Cancel the negatives out, e to the negative k over 5 is equal to 0.45. Again, sorry, I didn't realize I might have come off camera there. And so now how are we gonna get to the k? So what we're gonna do is we're gonna ln it, or log it, log e, ln. So if we ln e to the negative k over 5 is equal to ln 0.45, the e's cancel out, we end up with negative k over 5 is equal to ln 0.45. We then can work out, we take the 5 across, and the negative k is equal to negative 5 ln 0.45. Now, is that an option in any of our answers? Negative 5 log e, there you go, it's the first one. Unfortunately, none of these others, because there's no negative 5, and so the answer is going to be equal to A. 5A. You could have evaluated that and found out what the actual value is, but because our answer's on this format, we'll leave it at that. Awesome. Okay, so now we'll go jump into question 6. The temperature of a Formula 1 car's exhaust when entering the pits is normally distributed with a mean of 900 degrees Celsius and standard deviation of 100 degrees Celsius. We're going to assume that these are population parameters that they've given us. Find the probability that the temperature of a car's exhaust when entering the pit will be at least 139 degrees Celsius. So at least it's going to be a one-sided check. What we're going to be doing for this question is we're actually going to be doing our normal Z test, where we have x bar minus mu over sigma. We have x bar, or which the value that the x value that we're checking. Sorry, popping our x bar minus 900 the mu over 100. We can pop that into our calculators and find out what that is. 1039 minus 900 divided by 100, and that is just equal to 1.39. Now we have to use our normal tables to look up that value. I've got them here, so 1.39. Going to be looking at 13 all the way across, 0.4177. Okay, so we have a value of 0.4177. Now remember, what did we just look up? We looked up the probability from 0 up until there, but we want, the question goes, right? The question goes at least 139. So we want the other side. How do we get there? 0.5 minus 0.4177. I won't be able need to pop that into our calculator. So 0.0829, I think, is what we end up with. Oh no, sorry, 823. Do we have that as a possible answer? No. There you go. They drop the 3 out, we end up with E. So, question 6E. Perfect. Awesome. Okay, so that is question 6 done. Let's move on to question 7 then. So, the following: suppose a car accident in the Greater Cape Town area occur randomly at an average rate of 1 every 40 minutes. So we have a lambda. We have a lambda rate. Lambda is equal to 1 per 40 minutes. I'm going to adjust this immediately. Is equal to 1.5 per hour. So if we add 50% onto that to make it an hour, we've got that. We could possibly also do it per minute. Lambda is equal to 1 over 40 per minute. And so now we go calculate the probability that at most 2 accidents will occur in any particular hour. So now at most 2, so they want 0 accidents, 1 accident, and 2 accidents. How are we going to figure this out? Well, we're going to be using our Poisson distribution because we're counting the number of events that occur in a certain time. We've got in an hour, we've got a lambda per hour, so it's 1.5 per hour. That's our lambda. And we have our Poisson formula. Now, if you had a look at the answers or the possible choices, they're quite interesting. I think we're going to cut out E immediately because there's no choice, or to choose to, that does not fit in at all. We have lots of E's to the power of negative 1.5. Now, if we look at our Poisson distribution, you can see that there's an E to the negative lambda, and our lambda is 1.5. So in essence, what these numbers over here on the right refer to is going to be just the sum of these. Because remember, if we have multiple values, we can leave the E to the negative 1.5 in there and just multiply it by whatever this comes out to. So let's do that. Remember, we're looking for at most 2 accidents, so we're looking for 0, 1, and 2 accidents. We can do this immediately. E to the negative 1.5 times 1.5 to the power of 0 over 0 factorial plus, now e to the negative 1.5, 1.5 to the power of 1 over 1 factorial plus, 1 factorial plus e to the negative 1.5 is 1.5 squared, 2 factorial. This is equal to e to the negative 1.5 plus, that is equal to 1.5 e to the negative 1.5 plus, we might have to do some work here. We're going to have 1.5 squared divided by 2 factorial, 1.125, we have 1.125 e to the negative 1.5. You can see that I haven't evaluated the e's at all, and so if we sum that all together, we have 1, 2.5, let me do this, 1 plus 1.5 plus 1.125 is equal to 3.625 e to the negative 1.5. And I think if you've been looking at the possible answers, you'll see that C fits best. C is the exact thing which we just calculated, and so our final answer will be C. Perfect. Now moving on to question 8. Remember, the still keeps our lambdas all the same. It's the same information. If it is 12 p.m., what is the probability that the next accident will occur between 12:22 and 12:38 p.m.? So how are we going to do this? So I think for this one, because we're looking at minutes, we're going to make our lambda into per minutes. Remember, our original lambda is 1 per 40 minutes, and so our lambda for a minute would be 1 over 40 per minute. So we have a lambda. We now have to evaluate this exponential because we're looking at time between events occurring, time between accidents occurring. We're going to have 22 minutes and 38 minutes. For our 1 over 40 e to the negative x over 40 dx, if we evaluate that, that becomes negative e to the negative x over 40 for 22 and 38. So if we pop in the 38 first, we end up with negative e to the negative 38 over 40 minus the negative, so it becomes positive e to the negative 22 over 40. Now, is that an answer? If you've been paying attention, immediately A. A jumps out. A is exactly what we figured out there. So you've just had to evaluate the value at both ends. Awesome. So now let's move on to question 9. Which of the following experiments cannot be modeled using the binomial distribution for x? Oops. Roll a die 6 times and let x be the number of events or the number of even numbers observed. If you've been doing all your tuts and all the long workshops and all that, you'll see that we have done this a couple of times, and you can definitely model that as a binomial. So it can't be A. B, randomly select 5 pieces of fruit with replacement. That's a very important part. From a bag containing 4 oranges, 3 apples, and 2 bananas. Let x be the number of apples selected. So essentially you'd have the same probability for each time you pick an apple because there is replacement, and so the probabilities stay the same. And so B cannot be, because B can definitely be represented by a binomial distribution. Now C, toss a biased coin twice and let x denote the number of tails. Tossing a coin multiple times, you can definitely do a binomial because you're doing it twice. X being the number of heads, the number of tails. That's fine. D, randomly select 3 pieces of fruit without replacement. I think this is almost identical to B, however there's not replacement. And so one of the key components of the binomial distribution is that the probabilities are independent. The probabilities remain the same no matter what has happened. And because there's no replacement, the probability of choosing a banana or picking a banana will change each time you pick a piece of fruit. And so you cannot model this as a binomial. So the answer for question 9 is definitely D. Awesome. Let's move on to question 10. Let y follow a normal distribution with mean mu and variance 4. If we know that the probability of y is less than negative 10.5 is equal to 0.106, what is the value of mu? So for this one, we're also going to have to do some maths. So we have y follows normal with mu and 4. And we know the probability that y is less than or equal to negative 10.5 is equal to 1 or 0.106 or 10.6%. What is the value of mu? So the route that I'd suggest is I'd want to know what z value does that correspond to, because if we know the z value, we can use it to find mu, because we have x bar minus mu over sigma. We have variance. We don't know what mu is. We have an x bar, which is negative 10.5, but we don't know what z is. So how are we going to find z? Well, what we're going to be doing is we're just going to be looking up the corresponding value in the tables. But now remember, always draw your table. We're looking for the probability that it's less than negative 10.5 is 0.106, because it's looking to the left. So because less than, that's the error. We know it's less, it's going to be on the left side of the graph because the overall probability is less than 0.5. If it was greater than 0.5, it would be on the right side, but because it's less, it's on the left side. And so to find this value, we have to do 0.5 minus 0.106, which is equal to 0.394. So that's the probability that we're going to have to look up. If we jump straight into the tables, we're going to be looking for this value over here. So 394, I've got a 3, I've got a 9, and I've got a 4, 4. Okay, so we'll use that. And that works out to be 1.25. 1.25. Excuse me. Now remember, we've now looked up the positive value, but because it's on the left-hand side, we have to put a negative in there. So that's going to become negative 1.25. Starting on a new page, we then have negative 1.25 is equal to negative 10.5 minus mu over root 4, which is equal to 2. So to find out what that is, that becomes negative 2.5 is equal to negative 10.5 minus mu. We add 10.5 to each, and we end up with 8 is equal to negative mu. Therefore, mu is equal to negative 8. Now, is that a possibility in in the answers, and you can definitely see right away A is that answer. And so A is the answer for question 10. Perfect. Moving on to question 11. A 95% confidence interval for the mean number of people killed by a certain deadly disease is given by the interval AB. Which one of the following statements is true? The probability that someone is killed by the disease is 0.95. Nope, not quite right what a confidence interval refers to. If you recall the meaning, it's a confidence interval in which the mean will occur. So it's a range of values for which we'd like to see the mean occur. So the number of people killed by the disease is between A and B, and no, not quite. C, the probability that the interval AB contains the true mean number of people killed by the disease is 0.95. Now that sounds very, very promising. Let's have a look and see what the rest said, because remember it's only one. The probability that a person survives the disease is 0.05. No, not quite. The disease kills people aged between A and B with probability 0.95. No, not quite right. And so C is our final answer there. Perfect. Awesome. So now moving on to question 12. The song in Daniel's iTunes library vary in length, but have an average duration of 3.24 minutes and a standard deviation of 0.68 minutes. Daniel randomly samples 35 songs to listen to while traveling to school 2 hours away. What is the probability that his selection of songs will last the entire journey? I.e., he won't have to listen to any of them more than once. Okay, awesome. So we've got some information. We know that the mean for one song is equal to 3.2, and we know the standard deviation for one song is 0.68. So to find the mean and variance for both, we just have to multiply by 35. The mean gets multiplied by 35 straight away. So 35 times 3.24 is equal to 3.4. The variance, however, has to be multiplied by the square, but because they've given us the standard deviation, remember the square root of a square is just equal to the value itself. So we just multiply the standard deviation by 35 as well. So 0.68 times 35. This is equal to 23.8. So that is our standard deviation for 35 songs. Now, we want to know that his songs will last longer than 2 hours. 2 hours are 2 times 60 minutes, that's 120. So for our test, which we're going to be using, is going to be 120 minus 113.4 over 23.8 over root 35, because we're looking at an average, and the sample that we're looking at contains 35 songs. Was it 30 songs? No, 35 songs. Perfect. Okay, so we then have to find out our Z statistics. We have got 120 minus 113.4 divided by 23.8 divided by root 35. Perfect, and we end, oop, that does not look right. Oh yeah, sorry, I need to put in extra brackets. Boom, and we end up with a value of 1.64. Now remember, what value are we going to be looking at? We're going to be looking at 1.64, but we want to know the probability greater than. And so how are we going to do that? 0.5 minus whatever value we look up. So we're looking at 4.6416. We end up with 0.4495. So 0.4495. We're going to have 0.5 minus 0.4495, and that's going to be equal to minus 0.4495. That's equal to around 5%, 0.0505. Perfect. Now, there we go. That is our probability. Is there an answer to that? Let's have a look. We have A, and A jumps out, and it will be A. A is our answer, our 5% value.